Welcome back, students. In the previous lectures, we have seen how to solve an abstract problem and a job sequencing problem using greedy method. In today's class, we will try to solve a Huffman code problem using greedy method. In previous two lectures, we have seen how to solve an abstract problem and a job sequencing problem. In today's lecture, we'll try to solve a Huffman code using our greedy method. The primary application of a Huffman is a prefix code that's primarily used for lossless compression. It's used for lossless compression of data. The output of this Huffman code, once we run the algorithm, the output of this algorithm will be a variable length code. The output of the algorithm will be a variable length code. Let's first try to the normal conventions of storing these files is by using ASCII values of these files. These are 8-bit values. Say, for example, if you have a capital A, the ASCII representation of a capital A is a 65 decimal. And if I take the binary of this, it will be 2, 3, 4, 5, 6, 1, 0. This is a binary representation of the capital A. So essentially, what I'm doing over here in using these ASCII codes, that I'm making use of 8 bits to represent a single character. So if there's a message of 10 characters, then essentially I'll be using somewhere around 80 bits. This is too much of an information, or too much use of bits. If I could somehow reduce the number of bits that are being used, if I could somehow bring this down, if I somehow could optimize without losing any data, without losing any information, then that essentially will be a compression which is lossless. That will be a lossless compression. Let's take an example and see how we can do it. We'll take an arbitrary example to understand the lossless compression. Then we will apply the Huffman code and see the optimization or the minimization of these number of bits that are being used using Huffman code. Let's assume these are different characters that are there in my text or in my message. So I'm using character A, character B, character C, character D, character E, and character F. What we just saw is that the ASCII basically makes use of 8 bits to represent these characters. Let's take an assumption, or let's take an example wherein I'll be only representing these by 3 bits. So if I say 0, 0, and 0 to represent my A, and 0, 0, 0, 1 to represent my B, 0, 1, 0 for C. Likewise, I'm making use of actually 3 bits and 1, 0, 1. So these are the binary codes that I'm using for these. See, these are different characters that are there in my message. So these are the different characters, and what I mean by frequency is that how many times each of these characters appear in the message. Say, for example, let's take an example that my message is A, C, F, A, B, D, E, A, E, B. Take an assumption. This is an example. Now, in my example, if I see the frequency, so my A has 3 occurrences: occurrence number 1, occurrence number 2, occurrence number 3. My B has 2 occurrences. My E has 2 occurrences. So this is what I meant by frequency. So if I have to figure out the frequency of this, so A has a frequency of 3, E has a frequency of 2. Likewise, A has a frequency of 5. That essentially means that in the message, in the text, A appears 5 times. B has a frequency of 9, C has a frequency of 12, D has a frequency of 13, E has a frequency of 16, and F has a frequency of 45. These values mean actually nothing. They are not hardcore values. You can substitute any values in these places. They are just that how many times does an A or a B or a C or a D figure in my text. So this is a frequency. Now let's compute the number of bits that I need to represent this message, total bits that I need. So if A has a frequency of 5, that tells me that A actually has 5 occurrences in the text, and every single occurrence requires 3 bits for its representation. So we will be having a total of 15 bits to represent A. Let me say it again. A occurs 5 times in the text, in the message that needs to be compressed, and every single occurrence of this A requires 3 bits for the representation. So 5 times 3 bits each time is what I mean by this 15 bits. Likewise, for B, 9 occurrences of B, 3 bits for each occurrence gives me a total of 27 bits for B. 36 in this case. In this case it is 13 and 3, that's 39. In this case 16 and 3, that's a 48. And 45 into 3, that's 135. So total I'll be requiring 300 bits. So if I have to transmit this message, or if I have to send this message using this particular code, 3-bit code, I'll be requiring 300 bits. Let's do the same example. Let's try the same example using Huffman coding and see how Huffman coding can basically optimize or reduce the number of bits that are required in this case. Before we take the example, you may want to write down these frequencies, because I will be using the same example in Huffman coding. Let's try to figure out the different steps involved in the Huffman algorithm. 2 major parts. One is that you have to build a Huffman tree. This tree will be building basically using our input characters. The input that we'll be getting, that we'll be having, that input I'll be using to create this tree. Second, I'll have to traverse this tree, traverse this Huffman tree, and assign codes to characters. So this is how the Huffman algorithm, Huffman code will be working for us. First, in 2 major steps. One step will be that we will be building the tree, and the second step in this case will be that we will be traversing through that tree, and those traversal values, when I traverse, those traversal values will be used to represent different characters. The algorithm for building this tree is a 3-4 step algorithm. One, for every single character, for every single leaf node, say I had an A, B, C, D and F, for every single character, unique character, we will be using one leaf node for it. So step 1 will be creating a leaf node for every single character, for each unique character, and also we'll be creating a minimum heap. Why do I need this heap? I will explain it during the example. Second, out of these leaf nodes, whatever the number of leaf nodes I have, I'll be extracting 2 smallest possible. Extract 2 nodes with minimum frequency. Things will be much more easier to understand once we take the example for the same. Third, we'll create a new internal node and the sum of the value or weight of that will be equal to sum of two nodes frequency. So in step 3, what we are trying to do is that we are trying to create a new internal node, not a leaf node, but an internal node, and the weight of that internal node or the frequency of that internal node will be the sum of the 2 that we have already extracted. And we'll be repeating step 2 and 3 until heap contains only one node. That's where we stop. This will be our root node. Let me take you through this algorithm again. So what we are doing that in this is a 4-step algorithm. In this 4-step algorithm, every single instance of the character, every character that we have will be represented by a single node, a leaf node. It's more of a binary tree. So every single character here will be represented by a leaf node. Out of these, we'll be creating a heap out of this. The heap will basically keep track of every single node that we have there and the associated frequency of that node. Now out of this heap, I'll be extracting two nodes. Those nodes, the criterion for the extraction will be here, the frequency, the minimum possible frequency. The two nodes with the least frequencies, those are the two nodes that I'll be extracting. Based on these two extracted nodes, I'll be creating a new node. The weight or the frequency of this new node will be the sum of those two that have been already or previously extracted. I'll repeat this exercise, I'll repeat this process of step 2 and step 3 till I'm left with a single node in my heap, and that last node will be the root node. Let's try the same example that we tried earlier and try to solve it this time using Huffman code. Remember, in the previous example, we were in need of 300 bits. 300 bits were required. Let's try to see. Let's try that using Huffman code and see if we can reduce this number of bits. So let this be my heap. A had 5 occurrences. My B had 9 occurrences. My C had 12 occurrences. D had 13. E had 16 and F 45. This was the example that we used, and in the same example using 3-bit code we were in need of 300 bits. So let's say this is my heap. This is the heap that I have created. Out of this heap, I'm supposed to represent every single of these using a single node, using a single leaf node. The algorithm tells me that I have to extract two such leaf nodes with the minimum possible weight. Now if we see, the minimum possible weight here is for A is 5 and B is 9. So these are the two nodes with least frequency. So let's use these two nodes. So I have an A, let's write the frequency to make it readable, and my another node is B. The frequency of B is 9 in this case. That's step 2. Step 3 tells me that I will be creating a new internal node based on these two nodes. The frequency of that internal node now will be the sum of these two nodes. So the new node that I create, let's call that x1, and the weight that it will be carrying, frequency, is the sum of these two. So that's a 9 and a 5, that's essentially 14. This is a new node that I create. Since these two nodes have already been addressed, a new node has been created. So I'll be adding the new node in the heap. So x1 has been created with a value of 14, and these two I don't require now because they have already been addressed. Let's have a look at the heap again, and using step 2 I'll be extracting two nodes with the least possible value. Now the least possible value here is 12 for a C, 13 for a D, 14 for the new. We'll be including this as well. 16 for a E and 45. So obviously you have 12 and we have a 13. So these are the two nodes that I'll be selecting. So I have a C with a value of 12, and I have a D with a value of 13. That's my step 2. Step 3 tells me to create an internal node using these two nodes with the value equal to sum of these two. So that's let's call the new node as x2, and the weight on that will be 25 in this case. So we have created a new node, and let's put that in the heap, x2 with a weight of 25. These two we have addressed already. We are still not left with a single node. We'll stop once we are left on one single node in this heap. So we'll repeat step 2 and step 3. Again I have to check for the nodes. Now in this case my least two weights are E and the newly created internal node 14. So I'll be using this 14 and this 16 to create my new node. So this is my 14 and this is my E. Here's a weight of 16. So using these two, the least two possible, 14 and the 16. And remember, on the right hand side, the larger frequency will go on the right and the smaller frequency will go on the left hand side. So I'm creating a new node over here using 16 and the new internal node, and let's call this node as x3. The weight of x3 will be 30 in this case. Let's add x3 to our heap and we are done with these two. So we are left with 3 nodes. We have an f of 45, we have x2 with weight of frequency of 25 and x3 with frequency of 30. So these are the 2 nodes. These are the smallest possible least frequency 2 nodes. Let's create a new node out of these and let's call that x4. And the frequency of that is 30 and 25 will be 55. So we have addressed these two entirely new nodes, but we have created one more node, that's x4 with a value of 55. Okay, now we are left with the f with the weight of 45 and x4 with a 55. So let's take that f with the weight of 45 and based on these we'll create a new node, let's call that x5 and the weight will be 100. We have addressed this, we have created a new node, that's x5 with the weight 100. This is where we take our algorithm into the step 4, and step 4 tells us that if there's only a single node left, that single node is your root node, which is this one. So this is my root node. That's the first part of the Huffman code algorithm, that I have to build a tree. How did I build this tree? Is that I'm using these characters as the leaf nodes. Now you can check it out. So my A is a leaf node, my B is a leaf node, my C is a leaf node, my D is a leaf node, and my E is a leaf node. Also my F is a leaf node. The intermediary nodes that I created, they are all internal nodes. So this is the first part of the algorithm. Second part of the algorithm is that I have to traverse this tree, the tree that I just created. Let's traverse this. When I say I have to traverse this tree, what I mean is that I have to try reach every single node from the root node. Now there is a rule that I need to follow in this case. The rule is that if the traversal is on the left hand side, assign a 0, and if the traversal is on the right hand side, assign a 1. It's very simple. So if I traverse from root node, if I start the traversal towards left hand side, I'll be assigning on this path, on this traversal, a value of 0, and if the traversal is on the right hand side, then I'll be assigning a value of 1. So let's do it. F is on the left hand side, so I'll assign the value of 0. X4 on the right hand side, a 1. X3 is on the right hand side, so 1. Right hand side of x of 4. But x of 2 is on the left hand side of this, so a value of 0. C is on the left hand side of x2, so a value of 0. And D is on the right hand side, so a value of 1. Likewise here, for E, it's a 1. For x1, it's a 0. For B, it's a 1. And for A, it's a 0. So that was the second part of the algorithm. Now using this traversal values, using these values that I have assigned during my traversal, these are the new codes, these are the new variable length codes that I will be using to refer my characters. Now let's see, those characters are, let's put it here. I have an A, B, C, D, and E and F. These are the characters that I have. Okay, let's see A. If I have to reach to A, what's the path? The path is 1, 1, 0, 0. So that's the new code that I assigned to it. 1, 1, 0, 0. Check it again. To reach A from root node, I have to take this path. So this is the path. 1, 1, 0, 0. So this is the path that I am taking. And that's the code that I assigned to A. Likewise for my B, here, it's a 1, 1, 0, 1. 1, 1, 0, 1. Check it again. 1 to x4, then 1 to x3, then 0 to x1, then 1 here. That's 1101. Check it for C. This is my C. 1 0 0 1 0 0. It's a 3-bit code. So see, that's what I was trying to make you understand in the very beginning of the lecture, that these are variable length codes. Unlike the first example that I took, I use those fixed values of 3 bits, or in case of ASCII it is a 8-bit value, or in case of binary representation it may be a 5-bit value. But in this case, Huffman code, these are variable length codes. For my D, here's my D, it's a 1 0 1 1 0 1. For my E, there's my E, it's a 1 1 and 1 1 1 and 1. And for my F, it's a single character, that is 0. Here is a single path. Let's go back to the earlier example and check out the frequency of these. What is the frequency of each of these characters? So this is the code again, and this is the character. The frequency of each of these was A had a frequency of 5, B had a frequency of 9, C had a frequency of 12, D had a frequency of 13, E had a frequency of 16 and 45. Let's compute total bits. Now in the earlier example, I was using 3 bits to represent 8, and there were total 5 occurrences of A, so I had 15 bits. But in this case, I am making use of 4 bits to represent A. So 5 frequencies, 5 occurrences, so 5 into 4 is 20 bits. I'll be in need of 20 bits to represent my A in this case. Similarly for my B, 4 bits and 9 such occurrences. So every single occurrence will be requiring 4 bits. So for a total of 9 occurrences, I'll be requiring 36 bits. In this case, in the case of C, I'll be using 3 bits to represent C, and C has 12 occurrences in the text, so total of 12 into 3, that's 36. For D, 3 bits to represent a D, 13 occurrences, so that makes a total of 39. For E has 16 occurrences in the text. Every single occurrence is represented by 3 bits, so a total of 48 bits for E. And for F, which is the highest number of occurrences, I'll be using only a single bit, that means 45 bits. If I take the total sum of these, it sums up to 224 bits. Now remember, compare this value with the earlier computer value of 300 bits. For fixed size 3-bit values, we have a optimization of at least 76 bits. We are able to save 76 bits, and we did not compromise with the number of characters. So it's a lossless compression optimization by at least 76 bits in this particular example using Huffman code. Why the greedy? The greedy part here lies in this case that the one with the least frequencies, with the highest frequencies, the one character that has the highest number of frequencies, will be giving it least number of bits to represent. So if I see it the other way around, the one with the highest number of frequencies requires least bits, and the one with the least number of frequencies requires highest number of bits. That's how the greedy approach works in this case. This is how Huffman code can be used for lossless compression, and this is how to execute a Huffman code using greedy method. In the next lecture, that will be the last lecture for this greedy method technique, we'll be looking at an example or a problem of optimal storage on tapes. How do we store our information or data on tapes such that the retrieval ratio, the retrieval value of these programs is minimum using greedy method. Till then, take care.